Here we will see an application of the alternating series theorem. So the problem that we are faced with is calculating the sum, and which is the sum. Well, that's the sum which n equals 1 to infinity of minus 1 to the power n divided by n. With an accuracy, we should calculate this sum with an accuracy of 0.1, 1 over 10. Well, first of all, recognize that this is indeed an alternating series, since we have changing signs, right? Minus, plus, minus, plus, minus, plus, and the underlying sequence is 1 over n, and this 1 over n is monotonically decreasing to 0, right? So these are all non-negative terms, and the limit is 0. So we know by the alternating series theorem that indeed the sum as presented here does exist. Okay, but now we are asked to show that that we can estimate its sum up to 1 over 10. So first realize, so in summary, that this sum exists, right? So we can write S as the sum of n equals 1 to infinity minus 1 to the power n divided by n. And the alternating series theorem had a second component which said something about the quality of estimates, right? So what does the alternating series theorem say as a second, what was the second bullet? The second bullet says that the quality of the nth partial sum for this sum S has a quality of at least an plus 1. Right? So we know that S minus the nth partial sum, and now we use our knowledge about this underlying sequence an, we know that the estimate Sn for S has a quality of, has an accuracy of at least 1 over n plus 1. Right? So if we now would say, well, if 1 over n plus 1 is an upper bound for the accuracy, then we might take an n such that 1 over n plus 1 is smaller equal than 1 over 10. Right? So in that case, if we would pick such an n, then we could just take Sn as the approximation we strive for. Okay, so 1 over n plus 1 is smaller than 1/10. For instance, if we take n equals 9, right? So that would be the smallest n that would satisfy this condition, right? So then one of the suitable approximation is the estimation by S9, right? So we can S9 is the sum of n equals 1 to 9 of minus 1 to the power n divided by n. Right, so we may calculate it. It's a little bit elaborate, but okay, throw on your calculator and then you estimate, and then you can calculate the sum as the following. Rational number is minus 1879 divided by 2520. And if you just give an approximation of this, this is approximately 0.75. Okay, then what we later see is that we can keep on calculating and forming more accurate approximations in this way, but it's still not an exact value. Later on, we will see that actually the value of this sum is minus a log of 2, which is approximately 0.69.